Okay, we already discussed the rule of inference for proposition. Now, we are going to discuss the rule of inference for quantified statement. We are going to describe some important rules of inference for statements involving quantifiers. So, on this topic, some other rules will be introduced first, and then after that, we are going to solve problems using the rules of inference for quantified statements. Because these rules of inference are used extensively in mathematical arguments and often without being explicitly mentioned. And there are four kinds of rules of inference for quantified statements. The first rule is the universal instantiation. This is used to conclude that P of C is true where C is a particular member of the domain given the premise for all x, P of x. So it means that for all x, P of x, therefore P of C, in which C is any arbitrary member of the domain. So any arbitrary member of the domain. The second rule of inference for quantified statement is the universal generalization. Well, this rule states that for all x, P of x is true given the premise that P of C is true for all elements C in the domain. So this means that P of C for an arbitrary C or any element in the domain, therefore for all x, P of x. Now the universal generalization is used when we show that for all x, P of x is true by taking an arbitrary element C from the domain and showing that P of C is true. The element C that we select must be an arbitrary and not a specific element of the domain. That is, when we assert from for all x, P of x, the existence of an element C in the domain, we don't have control over C and we cannot make any other assumptions about C other than it comes from the domain. And the universal generalization is implicitly used in many proofs, and it is also seldom mentioned explicitly. However, the error of adding assumptions about the arbitrary element C when universal generalization is used is all too common in incorrect reasoning. The third rule of inference for quantified statement is the existential instantiation. The rule that allows us to conclude that there is an element C in the domain for which P of C is true if we know that there exists x, P of x is true. So there exists x, P of x, therefore P of C for some element C. We usually have no knowledge of what C is and only that it exists. But because it exists, well, we may give it a name C and continue our argument. So that is the existential instantiation. The fourth is the existential generalization. It is a rule of inference that is used to conclude that there exists x, P of X is true when a particular element C with P of C true is known. That is, if we know one element C in the domain for which P of C is true, then we know there exists X, P of X is true. So that is the last rule. So what are the rules? The universal instantiation, the universal generalization, the existential instantiation, the existential generalization. Now let's proceed to a problem or to a sample problem on how to use these rules for quantified statements. What does it look like? And how can we use these rules? Now, this is the example. Show that the premises everyone in this discrete mathematics class has taken a course in computer science, and Marla is a student in this class. Imply the conclusion Marla has taken a course in computer science. Now, let us first translate the problem to logical expressions. Well, of course, with quantifier, going back to our previous topic, which is translating from English to logical expressions, the first step is we rewrite the statement so that we can clearly identify the appropriate quantifiers to use. So the first one is everyone in this discrete mathematics class has taken a course in computer science. Second one is Marla is a student in this class. And the conclusion, which is Marla has taken a course in computer science. Next thing is to introduce the variable x. So our statement will become x is in discrete mathematics class. So x is in discrete mathematics class. And the second is x has taken a course in computer science. Now, if we notice, we just took the common words there, okay, which is in this discrete mathematics class and x has taken a course in computer science. After that, we're going to assign variables to it. So the first proposition is assigned to d of x, and then the second proposition is assigned to c of x. Since the statement would mean that all people in this class are students, then we can express the statement as for all x, d of x implies c of x. This will be the first premise, which is the first statement. Everyone in this discrete mathematics class has taken a course in computer science. Now, the second premise will be coming from the statement Marla is a student from this class. And since d of x denotes x is in this discrete mathematics class, which was assigned earlier, in the second statement, Marla is a student in this class means Marla is a student in discrete mathematics. So the second premise is d of Marla. These two are the premises. Now the conclusion should be Marla has taken a course in computer science. We already assigned c of x to the statement x has taken a course in computer science. And since x would be Marla, so the conclusion must be c of Marla. So this is the premise and this is the conclusion. Now, after establishing the premise and conclusion, we are now ready to prove its steps and reason using the basic rule of inference and the rule of inference for quantified statements. So place the step and reason then in number 1, write there the first premise, which is for all x, d of x implies c of x. Now, from the rule of inference, for quantified statement being introduced, what rule does it follow? Is it universal instantiation, universal generalization, existential instantiation, or existential generalization? What do you think? Okay, placing here the rules. Okay, we have here the rules and we have here the name of that rule. I place it here for us to review. What do you think is the rule that this premise follow? It states for all x, and there are only two rules that has for all. We can use the universal instantiation, okay, because it states that for all x, p of x, and therefore p of c, given that c is any arbitrary from the domain. And since Marla is only the value, then Marla is the value of c. So it becomes D implies C. So D of Marla implies C of Marla. And the reason becomes universal instantiation. Now in number 3, let's write the second premise, which is the D of Marla. I want you to observe steps 2 and 3. Is it a familiar rule of inference? Let us replace this one with variable so that we can remember the rule of inference that is being followed by these two. So let's replace 2 and 3 with variables so that we can remember what rule of inference is being followed. This will be P and this will be Q. Okay, since this is the same, let's just put P here. So P implies Q and P, therefore, what do you think will be the value? And what kind of rule is being used? What do you think? Oh, we forgot the premise. Okay, so that is a premise. What do you think will be the number 4? So the reason there, I know you have something in mind. It is modus ponens. So P implies Q and P, the answer is Q in modus ponens, which is the 2 and 3. That's how you're going to solve it. Now I want you to try this problem. Show that the premises a student in this class has not read the book and everyone in this class passed the first exam. Imply the conclusion someone who passed the first exam has not read the book. Please pause this video and try to answer. Okay, before answering the problem, let us first translate the premise and conclusion into logical expression. But first is we need to rewrite the proposition and assign values to it. So the first one is let C of x be the proposition x is in this class. Let B of x bx has read the book, and let p of x be x pass the first exam. Now, since the first premise states that a student in this class has not read the book, it is referring to a particular student in this class. So what quantifier are we going to use? Is it for all or there exist? So we are going to use the there exist x, c of x, and not b of x. So this is the first premise based from the statement a student in this class has not read the book. And then the other one is since, and the other premise states that everyone in this class passed the exam, so this will be its translation. So everyone in this class passed the exam. And since it tells us that everyone in this class is a person, then we are going to use this. And the conclusion will be there exists x, p of x, and not b of x. Since it states that someone has passed the first exam and has not read the book. Okay, that's the solution. Now we are going to solve and write the steps and the reason of the problem. Okay, so I just placed here the rule of inference for quantified statements and the rule of inference, which was discussed in the midterm, because this will help us be reminded of the rules. Now, the first step to do is to put the premise. So, the first premise is there exists x, c of x, and not b of x. So, that is the premise. Now, if we are going to look at the quantifier, there exists x. So, we only have two options, the existential instantiation and existential generalization. What do you think is the nearest rule that can be applied to this premise? What do you think? It is the existential instantiation. So, what will be the value? It will become c of a and not b of a, or any variable will do. So that is existential instantiation from 1. Now we already have c of a and not b of a. Now if we're going to replace these two with variable, say for example p and q, okay, so what do you think will be the rule of the inference that can be used on this step, p and q? So let's find p and q here. Okay, we have this. We also have this. Okay, so what do you think will be used for this? Okay, we can use the simplification p and q so that the value will be p. Okay, so what will be the value there? It will be c of a. So c of a is the simplification from 2. I know you have something in mind what rule can be used in step 2 and 3. Now, before solving this 2, let's write down the second premise. Actually, you can just write the second premise in number 2. It is also right to place the premise in step 2. Okay. Number 4, for all x, c of x implies p of x. That is the premise. And what do you think is the rule of inference for quantified statements can be used for this? So we only have two options again, the universal instantiation and universal generalization. So of course we can use the universal instantiation. So we can write here C of A implies P of A. That will be the universal instantiation from 4. Okay, now in number 6, we are going to use the modus ponens since step 1 and step 2 was already used, including step 4. We can now use step 3 and 5. So C of A and C of A implies B of A. We can use the modus ponens. So that will become P of A. Modus ponens of 3 and 5. So, and we have here left step 6. In number 7, let us use simplification. Well, we can also use the conjunction. In number 7, it's also right to use the conjunction, I guess. Not B of A. Okay. We can use simplification from 2, or we can use conjunction since simplification was already used here. And number 8, P of A. So number 6 was not used. Number 8, P of A and not B of A. That is conjunction from 6 and 7. So 6 and 7. And number 9 is there exists x, P of x and not B of x. That is existential generalization. So we can use the existential generalization here, which is there exists x, P of x. Why are we going to use the existential generalization? Because our conclusion is there exists P of x and not B of x. And since this is very close to the conclusion, we are going to use the existential generalization for us to get the conclusion. Okay, that's it. That is the step. Now, after watching this video, please email me so that I can give you some sample problems that you can practice. My email is nataliejoy@cmu.edu.ph. Please email me so that I can assess how you solve some of the problems that I'll be giving, and you can also submit me your solution.